Hello, and I would like to perform an example calculation for an RC circuit, RC being resistor and capacitor. This is going to be a direct current, and we're going to assume we just have one resistor, one capacitor, no battery or EMF source or anything else, and the wires are ideal. And we're going to assume that the capacitor is initially fully charged. So let's look at this problem. It says a heart defibrillator is used to resuscitate an accident victim by discharging a capacitor through the trunk of the patient's body. So the trunk is basically like the torso of the body, and it turns out we store this charge, and these paddles are meant to give a little shock across the heart to stop the heart and then hope that the heart restarts at its normal rhythm. If the defibrillator has a capacitance of 8.00 microfarads and an RC time constant of 10.0 milliseconds, what is the resistance of the path through the patient? Okay, so let's write down our knowns in the SI units. So we're told the capacitance is 8 microfarads. So let's write that down. Capital C is 8.00, and micro is times 10 to the minus 6 farads. We're also told the RC time constant, so let's write that down. Tau RC, that is the E-folding time, or the characteristic time, or the time constant, is 10 milliseconds. So milli is times 10 to the minus 3. So if we wanted to get this in seconds, I think this would be 0.0100 seconds. Because again, we would move the decimal point 1, 2, 3 places. Okay. We're looking for the resistance. Well, the nice thing about the RC time constant is that the RC time constant is exactly equal to R times C. It's almost what you'd expect, resistance times capacitance. Ohms times farads actually gives seconds, amazingly. So we should be able to get the resistance by division. So the resistive time constant, the RC time constant, or the E-folding time, divided by the capacitance should be the resistance. So let's put the numbers in. So this should be 0.0100 seconds, all divided by 8.00 times 10 to the minus 6 farads. Okay, so let's go ahead and get this value. Okay, and let's use the calculator. So let's clear that, and let's do 0.01 divided by, let's not worry about significant figures, at least in the calculator, 8 times 10 to the minus 6. Okay, and that's going to be exactly 1,250, so let's write that down. So in fact, this is equal to 1,250 ohms. Okay, that's a pretty large resistance. I mean, it's 1.25 kilo ohms. Okay, so the body does not allow a huge amount of current to go through it because there's a significant amount of resistance in the body. That is the trunk of the patient's body. B, if initial voltage is 12.0 kilovolts, how long does it take to decline to 600 volts? Okay, so we're going to say the initial voltage is 12 kilovolts is 12,000 volts, and we know that V final is 600 volts after some time. And we want to know what is that time that it takes to decay. to this 600 volts. Okay. Well, we also already know the time constant, and we also know what the resistance and the capacitance is. So, I want you to recall something that was presented in the lecture part of this unit, and that is, you hopefully recall that current as a function of time, the sketch should look something like this. So this we know to be exponential decay. Okay, exponential decay. Now I want you to also note something. By Ohm's law, we know that V is equal to I times R. But it should hopefully make sense to you that I is a function of time. And we know what that equation is because that was studied in the lecture. Also note that this V, if R is a constant, let's assume the resistance is exactly constant, that means V can be made into a function of time. But notice the only difference between V and I is really just this scalar factor of R. So I think that if we wanted to plot V as a function of time, it would also be basically exponential decay. Okay? Now one more thing. Do notice that we should be able to get V as a function of time by taking that electric current equation, which is exponentially decaying, and multiplying by R. So V as a function of t should be, now let's put in this expression for I as a function of t. That should be I initial e to the minus t over tau RC. There's the current, and we need to multiply that by the resistance. Okay, so there we go. Now, notice I times R gives V initial. Okay, so then I initial times R, this should be V initial. So what do we have? We have VO e to the minus t over tau RC. Okay. Now, we're told what V initial is. We're also told what V final is. So let's just let V final equal V at the t of interest. Okay? And what we want to do is we want to solve for this t. So we should say, okay, V final over V initial is equal to e to the minus t over tau RC. Now, this is isolating t. I hope if you are careful with your pre-calculus skills, you recognize what the next important step should be. Okay? So let me copy this onto the next board. Put this up here. Okay? Hopefully you're aware that in order to extract this time from the exponent, what we should do is we need to introduce the inverse function on both sides here. And so the inverse function of an exponential, the natural exponential, is a natural logarithm. So let's do natural logarithm of this ratio and natural logarithm of this. Okay, so the natural logarithm of VF over VO is ln VF over VO. And then the whole idea is that the natural logarithm of this exponential just gives the exponent because they're inverse functions. So it's minus t over tau RC. And then we should multiply by negative tau RC. So then this gives, up here, let's see, negative tau RC times natural log of VF over VO equal to t. And let's put the numbers in. So this is minus, and then tau RC was given as 10 milliseconds, so that's 0.01 seconds. Natural logarithm of V final, which I believe was 600 volts, yes. So this is 600 volts. The initial was the initial charge and voltage, that's 12,000 volts. And which is equal to T. Okay, so let's see how we can calculate this. So let's perform in our calculator minus 0.01 times, and we need the natural logarithm of 600 over 12,000. Close out the parenthesis. Enter. Okay, so let's write this down. So it's about 0.0299, almost like 0.03. Okay, so T is approximately 0.03 seconds. Notice that's approximately 3 time constants. So 3 e-folding, or 3 characteristic times. Okay. So, looks pretty good. And then lastly, C, find the energy stored on the capacitor as a function of time. Well, we know that energy stored in a capacitor should have one of 3 forms. It should be Q squared over 2C, or 1/2 Q times delta V, or 1/2 C delta V squared. Now we don't really know much about the charge on the capacitor, the Q, but 1/2 C delta V squared seems to be good because we have the capacitance and we have this function for delta V. We have that written down here on the previous board. So I think we can get the potential energy of the capacitor as a function of time, and that should be 1/2 times the capacitance times, and then delta V was going to be VO e to the minus T over tau RC. So this is VO e to the minus T over tau RC squared. Okay. Now, hopefully you recall that this is power of a power. So this is going to be multiplying powers. And then we're going to have C times VO squared. So this is going to be 1/2 C VO squared e to the minus 2T over tau RC. Okay. So that's fine for an answer if we want it general, but let's put the numbers in. So this is 1/2. The capacitance was, I think it was 8 microfarads. Yes, 8 microfarads. So this is 8 times 10 to the minus 6 farads and then the V initial was 12,000 volts. We have to square that. And then e to the minus 2t over, and then tau RC, remember, is 0.01. Well, let's see if we can get this to be just a little bit nicer. So a half times this squared, let's do that in a calculator. So let's do, let's see, 0.5 times 8 times 10 to the minus 6 times 12,000 squared. Okay, so that should be our coefficient, 576. So first off, our just leading coefficient should be 576. Now that should be the initial charge, by the way, because this exponentially decays as well, but a little faster. 576, that's units of joules. And then e to the, now let's see what 2 over 0.01 gives us. In fact, it's going to be negative 2, so it's negative 2 divided by 0.01. So it's negative 200. Okay, so let's write that down. And this is e to the negative 200t. Okay, so that's a pretty nice function. That's not so hard to plug in and use. Okay, so that's going to be the exact exponential decay equation for the energy stored in the capacitor as a function of time. In fact, with this factor of 2, it'll decay sort of, not necessarily twice as fast, but you kind of get the idea. I mean, it definitely in a more rapid rate when you consider the derivative. So thank you very much for your attention, and please smash that like button if you enjoy this video, and please subscribe to the channel to support it. Please share this within your sphere of influence, and I will see you in the next video. Thank you.